this invited talk. Am I well audible? Everyone? Okay. Well, my name is Montu Bhuvu, and the title of my presentation is Experimental and Modeling Investigation on the Application of a Structured Electrode in Improving the Process Uniformity in Plasma Enhanced Chemical Vapor Deposition. So this research is a part of a knowledge transfer partnership project between University of York and Oxford Instruments Plasma Technology in Bristol. And the entire project was funded by Innovate UK and Oxford Instruments through knowledge transfer partnership. I will begin by highlighting the overall motivation of this work, which is to improve the deposition uniformity in a PECVD tool for large diameter substrates. So if we look at the commercial plasma processing tool, it appears to be some huge machine like this, but the core part of this tool is a capacitively coupled plasma source driven by parallel plate electrodes. So in this schematic on the right hand side, you can see that the upper electrode is powered with standard 13.56 RF frequency, and it is in form of a shower head through which the process gas or ionizing gas is introduced in the chamber, whereas the lower electrode is grounded and it is in form of a table on which the substrate which is to be processed is placed. So the process actually takes place inside this chamber on the substrate, and here idea is to improve the process uniformity by controlling the uniformity of plasma around this substrate. So how we do it? So we use a concept of a structured electrode to physically control the plasma or process uniformity inside the system. Now, say if we use a conventional planar shower head, so this is a cutting view of a shower head, which is conventionally used in a processing tool. If we use the planar shower head, the CCP plasma formed between a shower head electrode and grounded table appears to be something shown in the below image. This is how the plasma appears inside the tool. However, now if we introduce a structural cavity inside the shower head in form of a rectangular trench, we can clearly see from the image that this provides a radial control over plasma ionization in the system. So with this project, the overall idea is to demonstrate the feasibility of this concept, whether we can use it to control the real process environment or not. The entire investigation consists of simulations as well as experiments. We started with very basic simulations in oxygen plasma. Then we performed some sort of experimental validation in test reactor, which is identical to the actual process tool. The simulations are carried out using hybrid plasma equipment model, which is accessed using Quantemol virtual tool interface. The simulation geometry that we consider is to be axisymmetric geometry, which appears to be something like this. We have a shower head electrode, we have a grounded electrode, and we frame this geometry inside this HPM package to replicate the plasma processing tool. We consider the capacity of plasma coupling between the respective electrodes. And we perform the simulation for two cases. Initially, we start with a simple case, oxygen plasma. We consider the plasma chemistry, which is well available in the literature. And then once we develop confidence with this modeling and experimental part, we try to simulate the process-relevant chemistries that we have accessed using Quantemol database. So the process-relevant chemistry that we use is the silent chemistry. The simulations are done in considering fluid kinetic approach. So we treat neutrals, ions, heavy radicals, and bulk electrons using fluid approximations, whereas the energetic secondary electrons in the system is considered using Monte Carlo solvents. So as I mentioned, we started with very simple oxygen plasma chemistry. And these are the different species that we have considered in our simulation for the case of oxygen plasma. We have neutral, excited, positive, and negatively charged species. With this species, the two main set of reactions that we consider is the electron impact reactions. So these are the set of electron impact reactions that are considered in the calculation. An important part is the reaction rates. So their reaction rates are determined by solving the Boltzmann equation for the given simulation condition. Whereas these are the heavy species reactions that are considered, and their respective reaction rates are considered from the literature. So we perform simulations for two different cases. One, we perform a simulation for conventional planar showerhead case, and then we introduce a structural cavity in the showerhead and run the simulation for same condition. So here, if we compare a case for 150 watt CCP power at 1.5 torr, we can clearly see that there is some sort of local enhancement in atomic oxygen density for the case of the structured showerhead. So in principle, this preliminary results indicate that we can have a radial control, a physical control on the plasma uniformity, depending on the location and the type of cavity that we introduce in the showerhead. So as a next step, something we tried was to quantify this result. And we performed some set of basic experiments in a test reactor. So this test reactor is identical to this PECVD process tool, but the experiments are performed in laboratory case rather than wearing the bunny suits in the process environment. So these experiments are performed in a similar scenario, 150 watt CCP power at 1.5 torr in argon oxygen mixture. So here the concentration is 1:99. So it's plasma is dominated by oxygen species. The reason why we use the mixture rather than pure oxygen is because we intend to perform the optical diagnostics through echnometry. So echnometry is a well-known technique. And we perform this optical diagnostics by capturing the images of the plasma through optical bandpass filter. So here, if we look at the images, these are the two images of a similar same plasma of argon oxygen mixture. So with this optical bandpass filter, we can capture the snapshot of the spatial intensity variation corresponding to the strong emission lines. So whenever we are having a discharge with argon oxygen mixture, we can think of two strong emission lines from the plasma. One corresponding to argon, which refers to 750 nanometer wavelength, which is the direct excitation of argon neutron. Whereas similarly for oxygen, it is 844 nanometer wavelength. So we use two optical bandpass filter. We capture these plasma images. And idea is that using this optical echnometry, if we take the ratio of these two images, these two intensity loads, we can determine the atomic oxygen concentration, knowing what is the neutral concentration of argon and oxygen, because we know that it is in the ratio 1:19. So since we have the information in form of image, using this technique, we can determine the spatial variation in atomic oxygen concentration inside the system. So these are the experiments that we performed. And now if we try to draw out a qualitative comparison between the experiments and the simulation, both the results indicate that there are some sort of this cavity effects which are reflected in the plasma. And if we take a radial plot exactly at the center of the discharge, both experiments as well as the simulation curve indicates that there is a peak exactly at the location of the cavity. So this builds up our confidence that inside the plasma we can control the plasma homogeneity by creating different types of cavities in the showerhead. So We extended this research by increasing the complexities of the simulation, wherein we tried simulating the process relevant silent plasma chemistry. And we used that simulation model to design the structured shower head. So initial experiment we did with just a single cavity. Now, knowing that the cavity is playing some role, we tried using this simulation model to design some fancy cavity shower heads to ensure that we have a better uniformity over the table region. And finally, we applied those designed shower heads for real process applications. So this is the silent plasma chemistry that we have access using Quantemol database. And you can see that there is a massive, huge number of species that we consider in the calculation. So this adds up the computational time. So these simulations are computationally extensive. But from the literature, something that I have highlighted in red color is SiH3 radical species. So from literature, it has been found that mostly on all the silane-based processes, whether it is oxide deposition, nitride deposition, or even amorphous silicon deposition, this particular species plays a significant role and governs the deposition process. So if we look at the electron impact and heavy species reaction, so these are the reactions that directly produce this SiH3 radical in our chemistry. And this is how we determine that, okay, if with electron impact reactions, if SiH3 is produced, then if we compare a simulation for a planar shower head and structured shower head case, it indicates that we can control the distribution, the spatial distribution of electrons inside the plasma with the help of, the radial locations and the aspect ratio of these cavities. And similarly, these cavities also control the spatial distribution of this SiH3 concentration inside the plasma. So as a next step, something we tried was, can we use this simulation model to determine the uniformity of the flux of these species over the table and optimize the design of this structural cavity? So what we did, we first selected a configuration. Let's use a 3-cavity configuration. And let's try to optimize the uniformity of SiH3 flux incident on the table over 200 ml substrate diameter, where uniformity is basically calculated from maximum, minimum, and mean values. And we can clearly see that if we compare the planar and structured shower head case, we can see a good improvement in the uniformity. So ideally, we want uniform line. We want a flat line whose uniformity is 0, right? But for the planar case, we can clearly see that when we consider the region from 150 mm to 200 mm diameter substrate, there is a rapid fall in the flux of these particles collected on the wafer. So this is something we term in process as the wafer edge effects, wherein the things actually starts to fall exponentially. But using these structural cavities, we can actually lift this falling profiles, and it's the reason why we can see some sort of improvement in the uniformity. So we performed several simulations, and we came up with this 3 suitable cavity configuration shower head, which theoretically, using simulations, they provided a better value of uniformity as compared to the planar shower head. So as a next step, we tried to test this structured shower head along with the planar shower head for the actual process environment. And the process that we selected was the silicon oxide process. So we deposited SiO2 film on 200 mm bare silicon wafer, and the recipe that we used was the mixture of silane, N2O, and N2. So again, it is a silane-based process, and the silane species play a significant role in determining this film deposition. So now, if we directly compare a planar shower head and the structured shower head mapping of the wafer, so this plot is the 2D representation of the film thickness which is being deposited on the wafer for a planar case as well as structured shower head case. And for the easiness of comparison, they are on the same scale right now. And we can clearly see that the cavities which are on the shower head are playing its role, and it is reflected on the process results, which is on the wafer. Now, if we consider just the radial flow, say from the center of the wafer to the edge of the wafer, we can see a substantial improvement in the uniformity for the case of structured shower head as compared to the planar case. So, why? Statistically, what we see is the uniformity is just the difference between maximum, minimum, and mean values. And for the planar shower head, the film deposition profile is somewhat like parabolic shape. We have a high deposition in the center and it falls over the edge. Now, using this cavity rings in the shower head, we can convert this parabolic profile into a sine or a cosine curve. Now, idea is to have absolutely a flat line, but sine and cosine curve are actually more close to a flat line as compared to a parabolic curve, because for parabolic curve, we can see that from 150 to 200 mm diameter region, there is a rapid fall in the thickness profile. So this film thickness uniformity is one of the key parameters that determines the overall quality of the process. And clearly, with the structured shower head, we can improve this film thickness uniformity. And another important process parameter is the refractive index of the film. So we can see a similar improvement in the uniformity of refractive index for a structured shower head case as compared to the planar case. Now, we are trying to compare all three structured shower heads that we have designed on the basis of simulation with the conventional use planar shower head for a range of operating pressures. And something that we see is like the structured shower heads A, B, and C, they give a good value of uniformity for a broad range of pressure. So in this plot, on the y-axis, it is the percentage uniformity, whereas on the x-axis is the operating pressure. And we are comparing a planar shower head performance with the three structured shower heads case for each pressure. For the case of planar shower head, we can see that the minimum value of uniformity is obtained only at a single value of pressure, which is 1.1 torque. Whereas for the case of the structured shower heads, consistently for a broad range of operating pressure, we get a good improvement in the uniformity. So this is the reason why the process engineer would be very happy to use this structured shower head. Reason is they have a broad process control window now. With planar shower head, the process control window is quite narrow, whereas with structured shower heads, they have a broader window. They have different possibilities of playing with parameters and develop a best process output. So here we are not improving the uniformity at the cost of the deposition rate. So if we compare the structured and planar shower head for these cases, we can see that almost the deposition rates are same for a particular case as compared to the planar shower. So finally, I will conclude this talk. So this investigation shows us that the structured shower head indicates improvement for processing large diameter substrates. Improvements are observed in terms of film thickness uniformity, refractive index, and a substantial reduction in vapor edge effects. We can have a better control over the process optimization because of this wide pressure window. And we can see a minimum rate variation with respect to planar shower head. So we are not sacrificing the deposition rate for improving the uniformity. So with this work, there were a massive number of references, which was not possible for me to highlight in a single slide. You will get the idea of all the references in the upcoming publication. But these are some of the key references that I would like to highlight, based on which I have carried out this work. And yeah, thank you for your attention.